Okay, so we discussed first order energy correction and first order correction in the wave function and last class, and this is the final form of the expression that we got for a particular state, psi n after the perturbation. uh, this is going to be the state, that is psi n is equal to unperturbed state plus this kind of a correction term adding along with that with the first order correction. Now what we have to do is to find out the second order correction in energy. As I mentioned in the last class, we will not be going to the second order correction in the wave function. We will be going up to the second order correction in the energy, and you will be coming to know that to calculate the second order correction in energy, you need to have the first order correction in the wave function. So this formula is a kind of a required thing for us to calculate the first order correction in the second order correction in the energy. So today second order correction in energy en2 ആണ് കണ്ടുപിടിക്കേണ്ട സാധനം. So the process of finding out this is actually the same. So we have an expression like this, h prime psi n1 plus h naught psi n2 is equal to en0 psi n2 plus en1 psi n1 plus en2 psi n0. This psi n0 is nothing but phi n. It's an unperturbed state, so we'll write it as phi n. So how do we get this expression? Actually, it's coming from the when you are comparing the lambda square terms in our perturbation expansion. Okay, so what we have done for finding out the first order correction in energy, the same process only will be doing. So for finding out the first order correction in energy, what we have done is multiplied the entire equation, not this equation, the previous lambda power 1, that expression with the phi n, and a term will be coming where you have en1 multiplied with the phi n, and if you multiplied with it with a phi n factor, this phi n bracket phi n will become 1, and you will be getting the first order correction in energy. So to do the second order correction in energy, you will do the same process, multiplying the entire equation with the bra phi n, and you will come to know that this quantity phi n is going to be 1, and you will be getting second order en energy correction. So what we have to do is multiply the entire equation with the phi, not with phi m, phi n. Phi n multiplying with the phi n, okay, it will produce something like first term h prime acting on phi n will be nothing but phi n h prime psi n1 plus h naught acting on phi n will produce e n naught, right, and phi n psi n2 will be there, which is equal to en0 phi n psi n2 plus en1 phi n psi n1 plus en2. next term will be 1. And what about this quantity phi n psi n 2? So we have seen already that this quantity is going to be equal to 0. There will be no correction along the particular phi n that we are taking. There will not be any correction in that particular direction. All that correction factor will be perpendicular to the already taking phi n. So let us take phi n as some number like phi 3. So it will be having the components which is coming from all 1 2 4 5 etc, but the 3 component will not be there along the same direction. The projection value will not be there, it's going to be 0. Same this quantity also, phi n multiplied with the second order correction, it's going to be 0. Same way this is also 0. All these 3 quantities are 0, which will give you En2. Second order correction in energy is nothing but phi n h prime psi n1. What is the psi n1? That is a first order correction in wave function, right? So this is our equation, second order correction in energy. The same process you can do for all other correction. Like if you want to find out the En3, you can do the same process, phi n multiply the equation, all other terms are going to be equal to 0, and you will be having En3 which is going to be equal with the phi n h prime. Here it will be psi n2 in that case. So we are right now not going to calculate what is the correction of phi n2. To calculate the third order correction you need to know phi n2. Without that it's kind of meaningless to have that kind of an expression. So right now we have understood what is the wave function correction in the first order thing. So from that we can calculate the second order correction in the energy. So En2, okay, let me substitute the value psi n1 here. Psi n1 is nothing but sigma m not equal to n phi m h1 phi n divided by e n 0 minus e m 0 into phi m. This was equation that we obtained for first order correction in the wave function, and here we have exactly the same term on this expression. So we can just substitute that value. So that will give you En2 in terms of known quantities. En2 is equal to phi n h prime. Here the vector term is going to be this quantity. This is just a number, right? This is going to be yeah. So okay, that sigma value you can put in front of this m not equal to n phi n. So here the vector term which is coming is phi m, that is multiplied with the okay, and that is the multiplication. Here the first term is phi m h prime phi n. En0 minus em0. So that is the expression. I think all the terms already came in. So you can see that phi m h prime phi n. Here what you have is phi n h prime phi m. This is just a complex conjugate of this quantity, right? So the entire term you can call this as phi m h prime phi n square. Sigma m not equal to n. This is phi m h prime phi n divided by en0 minus em0, this and a term square, right? Nothing else. So this is the second order correction in energy. So this is the second order correction in energy. Okay, you can put it on the box and give numbers. So last number was 13. I'll give this 14. And this is the now you got the second order correction in the energy terms. We can calculate the energy of the energy. What is the energy correction with this second order energy correction? Is going to be incorporating that state energy is going to be En is equal to En0 plus lambda En1 plus lambda square En2, etc. We will deal up to here. So this is En0 plus lambda En1. We have seen the term, which is going to be phi n HP phi n. That was the first order correction in energy. Nothing else, I guess. Yep. Lambda is multiplied with that h prime and it became HP. And next term is sigma m not equal to n phi m lambda square multiplied with the that h prime, it will become HP. Lambda h prime is HP, so it will become phi n divided by En0 minus Em0. This is the square of this term. En. So yeah, this is the energy equation up to second order correction, and it can extend the same manner to further number. So we will be dealing up to second order. So yeah, the series will go like that. Okay, so initially when we are discussing about the Hamiltonian or the validity of this particular non-degenerate perturbation analysis, we have seen that we have talked in terms of the operator, that our condition was like H. If H cap is the perturbed Hamiltonian, H naught is unperturbed Hamiltonian, and the correction is nothing but HP. If this is a case, so this HP has to be smaller than H naught. That was something that we have seen, and what it corresponds here on this series expansion on our energy equation. So ultimately, to have a good solution or good convergence for the energy equation, what we need to have is this series. It's a series expanding in terms of phi m HP phi n kind of a term. So it has to terminate as early as possible, right? So the whole series is getting expanded like this, that lambda h prime is uh, kind of on the energy expression, it's being uh, it is working like this term what you are seeing here. This is the effect of that particular operator. So how do this series converge? So whenever we are dealing, we will be dealing in perturbation analysis up to a maximum of 2. Kind of, we don't want to go further to get the solution, so it has to converge faster as possible. So to have a good convergence, what we need to have is this quantity in terms of what it is expanding, that quantity has to be smaller than 1. If it is anyway higher than 1, it's not going to be converged. So it has to be very small than 1. That is a kind of validity condition for our analysis, right? So this quantity phi m hp phi n by en0 minus em0 has to be smaller than 1. It's kind of our validity condition, huh? Okay, so yeah, now what will happen if the let's take two states. These are the energy equation down here is actually the unperturbed energy values of two different states. It can have unperturbed energy states. Two states can have same energy. In that cases you call them as degenerate state. So if there is degeneracy, what will happen from this expression is your denominator is going to be equal to 0 whenever two states are having same energy value. It is going to be equal to 0. That means the entire term is going to infinity and there is no convergence. So in that case we cannot apply here this kind of an expansion. That's why we are specifically mentioning this is for non-degenerate case. So degenerate case we have to use a slightly modified form of this analysis. So that's whole discussion of non-degenerate perturbation theory. You have to remember some of the expression like first order correction in energy. So first order correction in energies is having a simple form, like you know phi n, that is a non problem whatever we have, that non solution, exactly solvable solution, and there is going to be a correction term in the Hamiltonian if you want to approximate that quantity. So that correction acting on the unperturbed state phi n will give you the first order correction in energy. It's a simple form. What you need to know is unperturbed you need to know the perturbed Hamiltonian and which is acting on the unperturbed states. So that will give you the first order correction in energy. Second order correction, similar form, but you will be having different states on both sides. It's not phi m phi n, right? It's not phi n phi n, it's phi m phi n, and the square term will come, and you will be having a denominator which is en minus em naught em, yeah. So and the first order wave function correction in wave function also you need to know. So those things you keep in mind. So that will complete our first non-degenerate perturbation theory, and we have to solve few problems by using this particular analysis. So that's it.